Welcome to our 30th talk in the webinar series hosted by IEEE Malabar Subsection and in association with IEEE Malabar Hub on every Thursday right from June 4th, 2020. Today we have one of the eminent person from Regional Science Center and Planetarium Calicut, who is none other than Jayanth Ganguly. He will be talking on the topic robotics and its convergence in space science and astronomy. Before going into the topic, I'll introduce our speaker to the audience. Mr. Jayanth Ganguly is affiliated for the past 25 years to the Regional Science Center and Planetarium Calicut, which is functioning under National Council of Science Museum, Government of India. He is presently working in the capacity of Senior Technical Officer. He has conceptualized, designed and developed more than 30 astronomy programs for the planetarium towards educating the communicating astronomy and astrophysics among students and public using recent digital technologies in PowerDome and UniView platforms. He has also designed a large number of educational resources for short-term courses related to frontier scientific disciplines. He was instrumental in design and development of science galleries like Endurance Gallery, Astronomy Gallery, Ocean Gallery, etc., traveling science exhibition and also mobile science exhibition on contemporary scientific themes in the Science Center. He had organized several conferences, workshops, symposium towards dissemination of scientific knowledge. His main subject of interest includes astronomy and astrophysics, computer science and related technologies. He has authored several books individually or jointly, including a treatise on discrete mathematical structure. He has conceptualized a 2-semester course on astronomy and astrophysics, which is running successfully for the past 6 years. He has also published several articles, papers in some of the reputable journals like Planetarium, Propagation, Heritage, etc., and also popular science magazines. He was deputed by NCSM, Government of India, to Guangzhou, South Korea, as the India team leader to International Astronomy Olympiad Junior for the year 2011. He has an MSc and MCA degree in his hand. He has also pursued a postgraduate program on astronomy and planetarium science. He is an AMITE in CSE and executive committee member of Institute of Electronics and Telecommunication Engineers, IEEE for Calicut Subcenter. With this short introduction, I'll welcome Jayanth Ganguly to Malabar Subsection webinar series, and it's now over to you, sir.
Thanks, Dr. Sabik, for the introduction, and I also thank IEEE Malabar Subsection and IEEE Malabar Hub for having invited me for this talk series. Today's series is the 30th in the chain, and I am actually honored to be a part of it. So the outline of my talk will be somewhat like this. I will, since it is a heterogeneous group, so I will just give introductory remarks on what is actually astronomy and astrophysics all about, and then we will see the different categories of robots which are used in planetary exploration. We will throw some light on the historical and recent developmental aspects of orbital robotic systems. Then we will move to the surface robotic system. Again, we will speak something about its historical aspects and the recent developments. And then we will discuss something about how robotics and AI are aiding in ground-based observational systems. Next, we will discuss something about planetarium and its outreach activity using robotics in astronomy education. And then we will have a concluding remarks. So this is the total basic structure of this talk that we will be discussing today. So whenever we go out in the sky, what we see so many stars are there. So if you have been in rural area where there are less light pollution, you will see that the sky is flooded with a lot of stars, and every one of us actually are in awe and wonder when we see a lot of stars in the sky. So our ancestors were also very curious observers, and they saw that they could find out certain patterns in the sky, and this recurred. So to remember those recurrence and to help them in identifying certain portion of the sky, they actually imagined certain figures in the sky. The figures were in the form of some mythological being or some terrestrial being, and then people who like cats, they saw cats in the sky. People who like dogs, they saw dogs and horses. So there are dogs, horses, lions, and a lot of things are figured in the sky. But now today the Astronomical Union actually has classified the sky in different areas bounded by horizontal and vertical arcs, because in sky we just measure the circular angular measure, we don't have linear measure there. And so there are 88 areas in the sky bounded by horizontal and vertical arcs, and each of them containing approximately the figures which our ancestors have already imagined. And there are 88 areas. These are called the constellations. So this is a stick diagram of that. So these are some of the stick diagram of the constellations which we see. We have Bootes, Pisces, Cassiopeia. There are different names for the different constellations. These are the legendary figures which have been used by our ancestors actually to connecting the patterns which they have imagined in the sky. And there are a lot of Greek mythological stories connecting all these things. The next object which is of interest to us is the moon. All of us like the moon to sit under the moon sky when it is full moon day, but full moon is not good for astronomers because it floods the sky with a lot of light. But if you have had a chance to peep through a telescope when it is actually a part of the moon is illuminated, like a half moon or a quarter, you will see that there are certain very interesting features on the surface of the moon. Some are actually the dark areas which are called mareas, and some are there are depressions which are called craters, and there are certain areas which are actually highlands, and there are mountains and the shadows of mountains and crater depths. All these things can be seen, and you can see that there is a demarcating nearly straight line between the dark and the bright side. So that line from day and night, that is called the terminator. So we have all these aspects, and the moon is one of the important thing, and there are a lot of robotic missions which are attributed to the observing and knowing about moon. Then other class of objects which are of interest are the planets. So there are two classes of planets which we have classified. Some are rocky planets and some are gaseous planets. Among the rocky planets we have the Mercury, Venus, Earth and Mars, and then among the gaseous planets we have the largest planet, which is Jupiter, and the Saturn. It's a planet with the lowest density. Its density is in fact lower than the water. And then we have Uranus and Neptune. Previously we had Pluto. So all these bigger planets, that is Saturn, Jupiter, Uranus, Neptune, they are gaseous. They are mostly made of, though they have a solid core in the center, but they are mostly made up of gases. And then between this Mars and Jupiter, we have a band of lot of small objects floating in space, and they are called the asteroid belts. And then there are other objects in the sky which are actually comets, which are meteors, and all those things. So these all things from the solar system. So as I was saying about comets are actually spectacular celestial objects which are, if they are very near to Earth, and if they have actually the good tail, elongated tail. Actually there are two tails, the plasma tail and the ion tail and the dust tail. So if it is fully with tail and all, it is available in the sky, it is a very good sight. Amateur astronomers spend a lot of time taking photographs of those pictures of those comets. And then we have recently we had actually the comet Neowise, which was quite near to Sun also, spectacularly visible from various parts of the Earth. In fact from Calicut also it was visible, but mostly since there were clouds we could not see it properly. But in fact I myself have seen it as a somewhat as like a fuzzy band in the sky, and it could be identified as a comet. So with clouds also, since we were able to see, you can just imagine that if there would have been a clear sky and very good seeing conditions, how spectacular would have been. After I came to Calicut, say in 1994, I have seen a lot of good comets, a lot of spectacular comets like comet Hale-Bopp. I have seen comet Hyakutake was there, and these were spectacularly in the sky, and initially a lot of people came and observed this comet from the planetarium. Then the comet was there and everybody has seen the comet, so the period was quite long, and actually the observation also faded. So that was one aspect, that observing the comet. But scientists and astronomers, astrophysicists are more interested in what is inside a comet. So they sent robotic arms to actually to land on the comet and study the comet. The Deep Impact mission was due to one such mission to study a comet. Then there are other objects which are of interest, is the double star. Sometimes you see that two stars are in the same line of sight, though they may not be gravitationally bound with one another, but they are the same line of sight, so they appear to be very close to one another. They are called double stars. There are other volume of stars. There means, for example, a few stars scattered, but they are gravitationally bound, loosely bound. They are called open clusters. And there are some other group of stars which are closely, tightly bound gravitationally, and they float around hover over the center of our galaxy. They are called the tightly bound group of stars are called globular clusters. Then there are nebulas, the volume of gases from where actually which are the stellar nurseries, new stars get formed, and these nebulas, and some nebulas actually emit light, some nebulas reflect light, as we will be seeing. So this particular picture is showing you the Orion Nebula, which is an emission nebula because it has a star within it. It's very much inside that particular gaseous volume, and which actually energizes the gases and ultimately it radiates. So that is called emission nebula. Some nebulas, as I was telling, it actually reflect the starlight as the light falls on the surface of the nebula and it reflects it. So we see it is called the reflection nebula. And some nebulas actually has a lot of dust and gas inside, so it obstructs the light from coming out, and so we see a silhouette. So this is a horsehead nebula which is obstructing light, so we see the silhouette in form of a horsehead. And then there are some though it is called a nebula, another class of objects, but they are not actually the nebula in the sense which we were speaking about when we were speaking about the emission nebula or the reflection nebula. So they are not falling on those categories. This particular class of object, though it is called a nebula, it is not a nebula in that particular sense. So whenever a star evolves, actually it throws out certain materials from its surface. So what happens is that these materials are thrown out in space, but they don't just fly away. They are still gravitationally bound to the central star, and they are visible until actually the central star is not fully out of energy and they don't have any glow at all. So up till that star has a glow that illuminates the surrounding gaseous and dusty surrounding of that remnants which have been thrown out from the star, and they appear like a planetary nebula, from where actually we know that planets get formed. It appears like that. It is a planetary nebula with a central star in the center. So they are called as planetary nebula. Apart from this, if you would have been in a rural area where actually certain part of the year, if you see that there is a white band in the sky. Now, what is this white band? This white band is actually the density of star is so high, it appears whitish. For example, if you move in a train and if you see the nearby trees, you can actually see the individual trees. If you see far away in the mountain area or the field where actually you see greenery, you can't actually see the trees at all. So that is the continuum which we observe. So this continuum is observed in the if you have lot of stars and you can actually resolve through your eye. So that is what is that Milky Way. There are a lot of stars in that particular direction. All these stars belong to our own galaxy, the Milky Way galaxy. So like our Milky Way galaxy, there are different classes of galaxies. They have different shapes. Like we have galaxies which are elliptical shape, we have galaxies which are spiral shape. In fact, spiral shape are of different type. Elliptical shape, based on the ellipticity, are of classified under different categories, and there are some galaxies which are of irregular shape. So this is one of the normal spiral galaxy. This is our Andromeda galaxy. So we have galaxies in the sky. So these are the classes of objects we have in the sky. So based on all these things, actually whatever I have shown you, these are photographs taken in the visible part of the wavelength, that is 400 to 800, 700 angstrom unit. So we have that particular wavelength. But from the surface of the Earth, actually we get two particular slots of wavelengths in the electromagnetic spectrum: the radio band, the radio part, and the optical part, through which actually we can observe the sky from the surface of the Earth. Other wavelengths in the electromagnetic spectrum are absorbed, so we don't actually naturally see those through the detector from the surface of the Earth. For that, we have to either move through balloons to a higher location, higher altitude, or outside our atmosphere. So we can see from those areas, we can see in infrared, we can see in ultraviolet, X-ray, or gamma rays. So there are a lot of classes of spacecrafts which have detectors on those particular slots of wavelength, and we see the whole sky. And today, actually, we are in the golden age of astronomy, where we are flooded with data from all these detectors, and we get all these detectors, and ultimately actually we get a consolidated picture, holistic picture of what is the object about and what is the mechanism of the energy, and so we know the object in much detail than actually just observing it through the visible wavelength that we used to do. So next, before we move on to robotics, actually robotics in essence is a new entrant to this particular field of astronomy and space science and astrophysics. But before that, artificial intelligence has contributed a lot to the field of astronomy. Because see, as I was telling you that we were actually flooded, we are now flooded with lot of data from different detectors in space and on the ground-based observatories, and coping up with such a large data set demands a lot of technical aids and lot of algorithms which are intelligent to actually classify those objects, to find out the pattern, to find out to eliminate the noise and find out the signal out of it. So coping up with large volume of such data is actually not the cup of tea of the human brain. And so actually there are different mechanisms like neural networks which actually are used for data classification and image processing, and we have different expert systems which are used for large data sets, and we have large data sets, and all these AI aspects are used to aid astronomers and scientists to actually understand objects with which we are actually flooded with a lot of data. Now, specific to today's talk, we are actually seeing about the role of robotics on this astronomy, astrophysics and space science, that convergence. So the primary role of robotics are actually the different classes of robots which are up till now used for further studies and understanding them. So why are these robots used? In the sense that robots are used because if you send humans, what happens is that humans, once a country send an astronaut to space for a certain job, certain purpose, say repairing a certain spacecraft or doing a particular study in space. So space are normally not as safe as it is on the surface of the earth. In earth also we have a lot of disaster and calamities, but in space actually, since everything what is in space is not precisely at present also is not known. There are a lot of, even a small dust particle, it comes with a hit with a large momentum and it can damage certain thing. So it is always dangerous, and there are the conditions are many places are hostile, and it is not safe to actually, and it is quite costly to actually send a human from the surface of the earth to space for doing a certain particular task and then returning him or her back to the surface of the earth. Machines are quite handy, quite cheaper, and quite feasible, in economically and technically feasible. So people are actually viewing all these aspects, and the role of robotics is increasing. Though we have lot of robotics aspects in the terrestrial industrial conditions, like say iterative works of say assembling of a car or certain bikes or certain machinery, or iteratively means which repeated types of work or certain types of specialized work which are difficult for humans to do. Robotics is still used, but we will see the different types of robots which are used in astronomy and space science. So one thing is the robotic lander. So there are certain missions in space missions in which a robotic particular lander is made to land on the surface of a object and do certain tasks. And then there are certain robots which actually are mobile robots which moves on the surface of say Mars or Moon and certain things, or asteroid which lands on that and do certain functions. And there are penetrators which goes inside that particular object like a drill, and then it conducts certain tests to find out what is the tensile strength or chemical composition of that particular object. And then there are robotic manipulator arms which are actually used for certain movement of certain cargoes, or aiding astronauts to help in certain maneuvering work or certain repair missions. The next class of robotic system which we will be discussing is the orbital robotic system. So we will see the orbital robotic system. We will discuss something about its historic aspect, and the recent developmental aspects of that. So as the name specifically suggests, what is an orbital robotic system? An orbital robotic system is something where actually the spacecraft is orbiting a certain other body, and or it is in space and something is getting docked and doing certain job, say some repair mission or certain changing of certain instruments or fixing of new instruments or cleaning of certain optics or certain of that sort. and first of that was done in actually 1980, and it was called ARAMIS. So it was used for this particular robotic orbital system was used for rescue and servicing of malfunctioning spacecrafts. So it was a space application of automation, robotics and machine intelligence. That was the first time these all things were put together and put in an arm and used for a specific purpose. And then the first robotic manipulator, that is manipulator, we will come back to it, but the manipulator, first robotic manipulator was used in 1981 in STS-2, and later actually many of these manipulators were used for aiding humans who were astronauts in certain spacecraft like International Space Station or Mir or something of that sort, and where people were using these robotic arms for servicing the spacecraft like Hubble Space Telescope repair mission and so on. So before we move around, we will just discuss something about a toy model. You can see what is a robotic arm. A robotic arm is something like a arm which has say two different links. People call them as in the wrist and the elbow links, and they have different degrees of freedom. They are used through using servo motors and gears and all, and sensors are there which can turn and twist depending on the gear positioning, and they have different types of degrees of freedom by how many in space actually how many ways it can move and ultimately how much work it can do. So that is the robotic arm. So based on that basic principle which I have shown you as a toy model, we will see that some of the actual robotic arms which were used like Space Shuttle Remote Manipulator System, SRMS. So you can see the design of that particular arm. It has a two part. You can see it here. One is this part that is called as the shoulder arm and actually the elbow, and then there are for each of them there are actually pitch, yaw and rope. There are 3 degrees of freedom. So total we have 6 degrees of freedom. In that way actually this particular arm can move in different orientation in space and do certain works which are actually required. So the next video is showing you, this particular video is showing a Canada arm. Canada arm is actually a space station's remote manipulator system. It was mounted in International Space Station manipulator system, and you can see how actually this Canada arm was used to dock different types of spacecrafts which were moving and to the space station, International Space Station, either to actually send cargo to that particular space station. You can see that how these arms are actually attached to the mother space station, and how actually the other spacecraft which has come to the mother space station for docking purpose or transportation, how they are actually ultimately used in unison so that the particular mission is successfully taken up. So that particular aspect we are seeing in this particular video. You see that how actually the space station is getting docked to the main mother station of International Space Station, and then you can see that this docking process is occurring there, and then after the docking process you will see that how International Space Station is serviced using this docking, and that was one thing which were used for this particular mission. The next slide shows how actually this SRMS was used for an astronaut's activity in the space shuttle cargo bay. So you can see that how astronaut is attached to that particular space arm, and he is actually used to actually move this cargo in various locations. Apart from this, whatever we have discussed now, there were subsequently the development of special purpose dexterous manipulator. So dexterous manipulator has a special in the sense that it has a better grip. You can see in the design that it was used in space station remote manipulator system, and this is the dexterous arm, and actually you can see the way this grip is designed, and we will see a video where actually you can see how this grip is used. You can see that how the grip is rotating, and it is attached to how it is attached to one end of SSRM, and how it is remotely used for transporting goods. You can see that how this particular arm is moving through, and ultimately how it is delivering the cargo from the space station which has already come, spacecraft which has come to the International Space Station, where actually it is using its particular arm for delivery of this particular goods. So you can see the different types of detectors, different types of sensors, different type of movement of the arm. So all these things show that actually how this robotic system was used for aiding the astronauts for various types of mission. So next to that particular thing, we have the development of the European robotic arm. We are seeing here the European robotic arm, the ERA, which was used for International Space Station. Its design is shown here. You can see the outlay of the different sections of its design. It has a mass of around 630 kg, and it's a maximum load capacity of 8 tons. It had 4 identical CCD cameras which had integrated lighting and vision processing electronics embedded into it, and it can transport actually data and videos. Power can latch to gravel fixtures, and it can put mechanical forces and do a lot of work which will ultimately aid astronauts to actually do certain missions in space. Then Japan Experimental Module Remote Manipulator System, JEMRMS. You can see the design and these various aspects there. So it is a variation of what we have seen, and they were used on the ISS. Then the other manipulator systems like Robotics manipulator system is an onboard arm on the space lab, and it was first arm which was remotely controlled by space robots. So this is a different design. So up till now actually we were speaking about the robotic arms which were developed and which were used for aiding astronauts to do various jobs in space. Next class of robotics which have aided space science and astronomy and astrophysics is the surface robotic system. You can see that on the surface of the Mars certain tracks are formed. You can see from this picture like Opportunity was one such surface rover which actually moved on the surface of the Mars and the left tracks there. So Opportunity tracks in form of certain crater, Victoria crater. There are various names for various areas in the Martian surface, and similarly other tracks are also shown. Surface robotic systems, it started long back, and the first one was in 1970. It was not on Mars but on Moon. So we first aspired for the Moon, and in 1997 we had the Mars Pathfinder mission, on which the surface robotic system was actually the Sojourner. That was the surface robotic system which actually landed, and it gives us a lot of pictures and it did a lot of tests of the surface by moving on the surface of the Mars. And in fact many of the commands were autonomous, many of the commands were sent from here, but sometimes the decisions as we progressed in this particular field, so the spacecraft became more autonomous, in the sense that actually the spacecraft could actually take its own decisions by the inbuilt logic, and much of it was used in 2003 Mars mission, where Spirit and Opportunity, the surface robotic system, which ended each of its mission quite recently in 2019. It ended its mission, but each of them were there, and it has moved around to 5,000 meters on the planet, and it gave us spectacular pictures and did lot of tests, which actually people are still analyzing and trying to find out lot of data from that, but a lot of information from those data transmitted by this robotic arm. Then in 1970, starting from there, actually Lunokhod, it was built by Russians, and Lunokhod landed on Moon on 17 November 1970, and then Lunokhod 1 landed on Moon, and Lunokhod 2 landed on Moon on 16 January 1973, and these all moved around, and it gives lot of data which were useful for us. And then on 2003 we have the Spirit and Curiosity. The pictures are shown here. So now this is a Phoenix lander in 2008, a simulation of that, and you can see that how the lander came in there, how it was actually fallen. Actually one more technology was used, something like it will be falling through balloons, and then it will warm, and slowly the rover will come out, and this was one technique which Phoenix used and which was shown to you just now. And in this video actually I am showing you different types of designs people have worked on. You can go through this as it is being seen. You see the structure of the wheels which they are using, the number of motions which they are incorporating to make it more flexible based on which surface actually they are moving around. So some are using wheels, some are using spiky wheels, some are using circular wheel, some are using drum shaped wheel, some are using actually our JCB type of rollers. So designs are of different things, and people are working on that to actually get the optimum thing about, because where in what situation we can't actually, from sitting on the surface of the earth, we can't map the full thing. We don't have the full map, also detailed map in its minute details, so that we can't actually get the full idea, full knowledge of that is yet to come. So you can see the different design which has been used for different types of robotic arm, which has been shown here. So they were the different technologies which are shown to you, and you can see that sometimes what happens is that it goes in the it supports on the surface, and exist or any organic compounds are present there, or in that sense whether any type of water has flown or will be flow, means any type of things are there. So all these things they are doing it autonomously, and they are finding out. So a rover, surface rover design, surface robotics, landers design are the prime important things which space scientists aspire to do, new designs. In fact, we had a planetarium show here which was showing a SpaceX mission, where actually there was a competition where people will design a robot and they will make their own spacecraft. They should not be government funded, and then it will be transferred to the moon. The spacecraft will take the rover to the moon. It will get down and it will hop a few number of times. It will go cover a certain distance, and they will send the photograph and the winner. People have tried that, and so this is one of the most challenging thing which youngsters who are in the field of mechatronics, who are in the field of mechanical engineering, electronics, computer engineering, they can aspire for. Then one more important thing is that comets. As I was telling you, that from Earth actually comets are fine, that you see them, they become bright. In fact, we had the comets frequently coming on our sky, frequently in the sense that they come. Sometimes they are periodic, sometimes they come and they are predicted, they are seen. And Neowise was one of the comet which were very much in news in Calicut also, and I also saw it once, though it was mostly cloudy. I myself and my boss, we went there and to the Calicut beach, and we saw that. And it is good to observe this comet, photograph it. But then what is inside a comet? By remote photography is not sufficient. So people thought that to understand what is a comet, there should be a lander which will crash land on the surface of a comet. So like that one mission was, in fact one Hollywood movie was also made, you can see that. But then there was a mission called Deep Impact to reach to comet Temple 1. It actually made the thing on 2000, made the landing on 2000. It was launched in 2005 and it landed on the comet Temple 1 2007. It was there for a certain duration of time, but then it fell into a crater and its power went away due to shadow of the crater, and the mission has to be abandoned. But really it did lot of work. It penetrated, it drilled, it found out a lot of things, a lot of data about the chemical composition, about the structural details of the comet, and our knowledge has really gained due to this robotic mission to that particular comet. So then there were now the comet was there, robotic arm is there. These are the very two things. What other things like computer vision in astronomy? Now you are seeing that we have detailed pictures of the Saturn's ring, the gaps between that. We have to have highly resolved pictures, and not only that, we have to be more specific about what all things are there. So some pictures are taken from Earth-based observatories, but more close-up pictures are taken from near flyby. So these flyby missions are also planned in such a way that we get close-up pictures, and the computer vision technique is used to the maximum to capture because the time is less. This flyer will just fly by a particular astronomical object, and we have to gather the information as much as possible in that flyby time. So we have to take the data. It should not be a junk data. It should be not, there should not be redundancy, and then it has to be transmitted to the Earth station where we will be analyzing. So this is one of the picture, and you can see that there are other pictures like radar thing of Saturn's moon Titan. While we know that Titan, there is methane rivers flowing in the Titan. Like that, people have found out how they do that. So one thing is that they send radar waves and then they get the reflected waves. So some of these things are done during flyby missions, and these images are constructed through those data. So you can understand that lot of technical know-how goes into how to get those data and how to clean up those data and ultimately get information from data. Then we have the Venus. So you may see Venus is a morning or evening time. Say in these days it is in morning. So you can see Venus as a bright object in the sky. Venus is whitish and very beautiful to see, but whitish to white is because it has a very dense cloud of carbon dioxide. In fact, inside Venus, what happens is that there are sulfur dioxide and sulfuric acid rain is there, and in fact, you can't just put a rover and we try to put a fly down object through the atmosphere, but it just survived for I think some 50 minutes. After that there was no signal from that. So but based on radar observation, based on various parameters, we still know a lot about the surface feature on the Venus. We can recreate those, though we have not gone there. We can recreate those whatever is there on the surface of the Venus, or on the under the surface of the Titan or Enceladus, which are the hot places of interest for astrophysics or astrobiology, or knowing about our own solar system. So that was one thing. Where else we have more requirement of this, our artificial intelligence, machine learning? So there was a mission called Kepler mission. Now Kepler mission, we found out a technique that by transit, that is an object, a moon or any object, if it passes in front of a star, it is called as a transit. So the planets of a particular stellar system crosses the visible disk of a particular star, we get a drop in intensity of the star, and that drop in intensity is enough to actually calibrate and find out the size of the planet, the orbital parameters of the planet. So, and we know about the dynamics of that. So Kepler mission was one such mission which was envisioned, and again computer vision and all the data collection detectors and all the technologies were put into test, and we have a flood of data from this particular mission, and people are astronomers are analyzing that. Then we have the International Space Station, but then International Space Station, Hubble Space Telescope is there, which is actually searching the sky, and since it is beyond our atmosphere, it searches the sky for actually different types of galaxies, or galaxies which are so low in intensity that our atmosphere never allows us to see those. So these types of telescopes, which are actually space telescopes, that is called, they are placed outside our atmosphere so that you can see total space around well, and they can photograph, capture data, and give us information about it. Now the Hubble Space Telescope is fairly long, and one more space telescope of that sort, which is called James Webb Space Telescope, named after one of the space administrators, first administrator of NASA. So but it is a gigantic space telescope, and it has ultra-modern techniques and technologies used in it. People say that it will fly through solar sail, that is the solar wind will make it fly. Its fuel consumption will be very less, and it will go far away, and it will give us a lot of data from that. So this is using a lot of robotics, AI, and all those things goes into the design aspect of this. Apart from this, we will be showing you this particular, just observe this video, that on the ground based we are using telescopes. Now telescopes are nothing but actually they have optical elements like a mirror or a lens, which collects. The front one is called the objective. The light comes and falls in the objective, then falls back to a diagonal, and then based on the design, it is made to fall on an eyepiece, where on a side eyepiece, where either an eyepiece to focus it on our eye, or it is made to fall on a detector from which it is recorded. So this is the full theory of a telescope. Now what happens is that due to scintillations, due to refractions, sometimes the data goes, and robots are actually used to please those the big mirrors are actually made, and in which small segments are made, and nano robots are made to actually move around and sense the photon from where it is coming and align itself. So this is one of the videos which I have shown you where actually this technique is used. So that is one thing. And then we have other things, like when we have, you can see that when we are doing observations from an observatory, our atmosphere gets heated up, and due to variation in the temperature, there is a temperature gradient, due to which actually the image which we get of the remote objects on our telescope, through our telescope, is not very accurate. Because why it isn't accurate? Because of the different densities of the, so because of this temperature gradient, density fluctuate, and the light which comes from a particular stellar shows move around to our, so it doesn't converge at a particular place. So for rectifying this purpose, or rectifying this particular thing, technique called adaptive optics is used. So this video was showing you that particular thing. It is also showing you now. What happens is that first a laser beam, a sodium laser beam is shown as it is shown now. So it is shown a sodium laser beam is made to pass in the direction where we want to observe. So when the laser passes through our atmosphere, it excites the actually atmospheric atoms which are in the line of the laser, and due to this atmospheric atom, it actually creates a disturbance on that, which forms an image on the telescope. So the telescope by its own algorithm negates that particular thing. It gives a negative curvature or whatever it is to the shape of the waveform which is coming in, and which is added to the original light which is coming from the object. As a result of which, what happens is that we rectify the image which is coming out, and we get the encoded correct image of the particular object. So accordingly, what happens when this negative curvature is either given, it is given through actually actuators which actually drives the small element of the big mirrors, small elements. By what I mean by that is, nowadays people don't make very large single mirror. So they make a large diameter mirror, but they are made up of small number of sub mirrors. Like we have hexagonal sub mirrors pieces, which makes actually it's like a honeycomb structure. So what happens is that each of these, as it is shown, that each of these honeycomb structure can be individually controlled and compensated for any change in the waveform. So that gives rise to a new optics, and that is called the adaptive optics, and that was shown in this particular video. So when we speak about so much about robotics, AI, and myself working in planetarium as such, I can't avoid the machine which we use here, and that uses also a good amount of artificial intelligence and robotics. So what is a planetarium? A planetarium is a device. Classically, actually, it is a device to recreate, simulate the night sky for education, not only for education, for general public. In fact, astronauts are trained in a planetarium, navigators are trained in a planetarium. We learn different phenomena in a planetarium, because a planetarium can exactly create what will happen, say 5,000 years from now, or 5,000 years back what happened. So the planetarium instrument is of that sort. So you can see that the structure, there are 6 degrees of motion catering to the different types of motions, like diurnal motion, annual motion, precision motion, azimuth motion. There are different motion giving rise to different structures, and an instrument which is an optomechanical instrument which is made, and which is still not indispensable. Actually, still digital technologies exist. This is just for your completion sake. I have put the different types of projectors and gear systems which all exist there. And though digital technologies exist, but still digital technologies are not yet fit enough to create the same effect as an optomechanical system which are used. A digital system actually make a mosaic system. They are using, for example, we have a hybrid system where optomechanical and digital systems are there, and all combined together to recreate the night sky or the graphics. If you are going through inside you can recreate that. There is a thing called Power Dome software which can split the image and stitch it all digitally done, and or wherever curvature is required, it gives the curvature, and you see the planetarium as you see when you visit here. So we have different. This is one of the projectors. We have 9 projectors and the optomechanical device which I have already shown you. So based on all these things, so this is all about the hybrid system. So I have given you a nutshell about how astronomy, astrophysics, space science, and robotics converge together, each helping other. Not only robotics, AI in general, and machine learning. All these things are very handy, and lot of engineers, lot of scientists, lot of people are getting attracted towards this particular field to know the universe much better. Caption in the top that sky, whatever we see, is just the lower limit. There is lot to see beyond it. Thank you.
Hello.
Yeah. Finished.
Okay. Dear participants, if you have any queries, you can put it in chat, or either you can unmute and you can ask directly. Yes, Mohit, you can unmute and you can ask. No problem.
Yeah. Please ask.
Sir, is there any scope of becoming an astronaut in India after the BTech or doing an engineering?
You want to do astronomy after engineering? That's what your question is, I think. Is it? Is it what you have asked me?
Yes.
Yeah. See, I will tell you that. Of course, you can do you can directly enter PhD in astrophysics and astronomy directly after your BTech. You need not do an MTech. If you want to do a PhD in engineering, you have to go through MTech. But after your BTech, you can sit for just examination. Or you can sit for GATE examination, and you can apply. If you have qualified, you have to sit in the physics. Whichever discipline you are, so mechanical, electrical, electronics, it doesn't matter, but you have to sit for the physics part of the test. And if you qualify that, you can apply in IUCA or NCRA, National Center of Radio Astrophysics, or Indian Institute of Astrophysics, and you can directly enroll for a 3-4 year program in PhD, and then you can go for a professional career in astrophysics and astronomy. Actually, GMRT in Pune, near Pune, they have a lot of radio antennas they actually maintain and they design. Govinda Sharup was the person who designed with a lot of his engineering scientists under him, engineers and scientists with him. And I think a lot of engineers are coming up in the field of astronomy. And you can see that robotics and AI are actually flooding this field. So you can.
One question is there.
Yeah.
Shall I read?
Yeah, please. I can see. Why does billion of dollars keen to send people to Mars when sending robot would be yield the result? Yeah, it is something like, see, it is a personal wish. Actually, sending a person to a remote location is like means if Elon Musk wants to send, or Elon Musk wants to go there, it is something very personal to him, that he wants to take up the challenge, the risk. That is something very specific to him. Like if you can always know about Mount Everest top by passing in a jet over it, but people climb it and then conquer the Mount Everest. So in that same sense you have to take, though this is cheaper and technologies are getting developed, but well, people because we have though robots were deployed to study the moon, but Americans thought that yeah, our person will first go and land on moon. So that is something a different thing. Okay. And then what we have, you have said about Kepler's telescope uses transit method. If the planet is too small, then it won't be difficult to detect. No, actually, the reason if it is small also, its detectors are quite powerful enough to detect minute fluctuations in photons. Okay. So that is the reason Kepler was very successful. There are other methods also, Wobble method and other method, but Kepler's method is a very time-tested method, and lot of exoplanets have been found out with that. Okay, is Mars colonization easily possible? No, it is not possible. It will take a long time. Even our moon going, it is difficult now. So Mars will take a long time.
Hello, sir.
Any other?
Sir, am I audible?
Yeah, Ishan, carry on.
Yes. First of all, sir, thank you for the fruitful insight that you gave on space technology and for the future. I have two questions. One is regarding space mining. That how do you think it will be viable in the near future, and what's the scope for it, like as a career or as a scientist or an astronaut, or what's the idea for space mining?
Yeah, I will answer this first. Space mining, as I told you, that it depends on the technologies, different types of technologies. Actually, they were using drilling technologies, and based on which actually you have to make the design so that it has to land and it has to find the appropriate surface. It has to drill. How much it will drill also has to be initially modeled theoretically, because after sending you can't just sit around and see your money going wrong. So everything has to be modeled. Challenge is that people are working on it, but then there are other remote sensing technologies also which are coming in, like spectroscopy and all those things, to remotely monitor the surface and try to get what is under the surface. So there are various people are trying it from various dimensions, and of course everything is fascinating, and if you are good enough for a particular design, it is a good career. There is no doubt. A lot of people are employing, a lot of agencies. ISRO is giving good amount of money to a lot of scientists, and they are paying quite well. And other than that, also our outside agencies like NASA or other space administrators are also paying quite well. So the career-wise, it is not a bad option. But the scope is a bit narrow. It is not like our normal engineering jobs, which floods the market. But still, there are ample scope for that. Yeah.
Yes, sir. Thank you, sir. And my second question is: earlier this month, the Israeli Space Security Chief, former, said that there is some sort of galactic federation and the US astronauts and the space agency are in contact with them, supposedly aliens. So, what do you comment on that, sir?
These are actually, unless it is setting, these are very difficult to comment because most of them are hoax. So many times it has found out that people have found certain signals, and then ultimately they found out that they were from some other sources. So it has to be verified, and people has to come out with it. Solid evidences has to be there. We have to wait and see. That's all.
Thank you, sir. Thank you so much, sir.
So we had one more question. What is the maximum range of the Kepler telescope in space?
See, by range actually it can detect very faint light, in the sense that a very distant worlds also it has detect. So when you detect optics, you don't actually, theoretically it has infinite range, but there are limitations because there will be attenuation, there will be other obstacles which absorbs light when it comes, photons when it comes through space. So those things are there, but otherwise actually if there is a light and if it can travel, because light photon travels in space. So it is not that I am watching something. What happens is that a photon has to come and hit the detector. So any photon can come and hit the detector. So we can't speak about this, and we can speak about sensitivity from the surface of the Earth. In space, actually, since it is vacuum, it's not good enough to speak in terms of sensitivity. The electronic limits work there in rigid conditions like cool temperature and all, how this electronics behaves. So these all things are subjective to it.
Okay, sir. Thank you. Like we have no more question. Anyway, we have the time limit up to 6:30. We have finished that one. We have covered 5 more extra minutes. Okay. Before that, I would like to tell, like, feedback link is being shared in the chat box. Participants can fill it out for availing the certificates. And it was a wonderful section. Covered the aspects regarding the robotics, its design, its structure, its different forms, which will help in space science technologies. I think it has benefited the participants who are interested in doing astrophysics or astronomy, or want to work with space science. They could take this particular subject. Thank you once again. So, on behalf of IEEE MSS, I would like to thank our resource person, Jayanth Ganguly, for accepting our invitation and giving a wonderful talk over here. I also thank all the participants who have joined here to attend this workshop, this webinar. Thank you once again on behalf of IEEE MSS.
Thank you.